Okay, welcome to week 3, where we're going to build a pyramid, we're going to create our own shader class, and we are going to add transformations to our objects and have a basic camera in the scene. Now, if you haven't been following along, this is going to build off of our previous ones. Our last one, we went over shaders and basic vertices, and the first one we went over just setting up our project, importing libraries and all of that stuff. So be sure to follow from week 1 to week 2 and now week 3. So the first thing we're going to do is we're going to create a shader class. We're going to take our shader, we're going to move it out to its own class, and we're actually going to also read these shaders from a file. Before I do that, I will actually go through and set up Visual Studio to work with all of these files so that you can see how I would continue what I was doing in CMake into Visual Studio. It's not a big difference. It's actually very simple. What else? And then we're going to set up the camera. We're going to give our meshes positions, and we're going to create our not a pyramid, a cube. So I'm going to try to make this a quicker week for you. It shouldn't take as long for the theory part of it. It should just be a lot more application this week on top of everything we've gone over. So I'll stop talking now. Again, be sure to join the Discord that I'm going to link at every one of these videos now that I remember to link it in my intro. Let's just jump into it now. Okay, so before we start, I did not create a commit, so I'm just gonna create a commit on this shaders mesh class triangle. All right, that should be good enough. All right, so what do we need to do? First thing we're gonna do is we're gonna create our own shader class. Now, why do we want to create our own shader class? The reason we want to create our own shader class is because really, you want to reuse shaders in a real world application as often as you want, as possible. In many instances, and our application being a perfect example of it, you only need one shader if you're not doing anything fancy. In our application and everything you do in this course, you're only ever really going to need one, maybe two shaders, because I think they want a visible light source, but maybe two shaders. But in general, almost all your objects are being drawn with a single shader. So we're going to separate out the shader stuff so that we can we can make editing shaders easier. 2, we're going to need to be able to set data on a shader. So you might be using the same shader for all of your objects, but you're going to be setting data on your shader before making your draw calls, right? So that's what we're going to do today. So we are going to create our own shader class. So we are going to, before I create the own shader class, we will open this project in Visual Studio and get this running in Visual Studio just to show you how it's done. It's going to be pretty simple. We're going to we're going to add the files that we did not add last time. So I guess it's going to be the mesh class and the types.h. So add existing item. Again, we're going to go into our include. We're going to add both mesh and types. In our source, add existing item, source, just the mesh class here. And then we need to, if I am correct, bring in GLM. Where's GLM? It's in types, I think. Yeah, GLM. We need to do our GLM folder, so we'll do right-click it, properties, VC++, include directories here. Go here, edit, and then we will just add the exact same thing, shared, glad include. We will do this, but it will literally just be GLM. And now that, I believe, is all that's needed to make this run. And we have exactly what we had before, but running in Visual Studio. So that's how you do this in Visual Studio compared to what I did before. It's going to be the same process pretty much throughout the entire class. I don't think we're adding too many more libraries. I think we might have hit our library limit for the course. So we might not have to actually do too much in here ever again. But that's how you do it. I'm going to save this, and then I'm going to commit it to my repository. Commit update VS solution. Okay. Now that that's done, create our own shader class. We're going to new C++ class shader. We add this to GitHub. We're just going to move our CPP into our source folder. We're going to replace this with pragma1. I've been meaning to go in and change how they auto generate stuff. I don't like those, but and here instead of doing it that, we'll do this. All right, and then we reload the CMake project for it to pick up the CPP file. So that's our shader class. Now we are going to call shader. It's going to have a few public functions. So we're going to be able to do things in two different ways. We're going to be able to do, we're going to use the file system API. So in C++, I believe it's 17, it might have been 14, they introduced this file system API. The reason we're using this is so that we can differentiate some things here. So we're going to create a using path equals std file system path. And I do this just so I don't need to write path all the time. And actually, we're going to cheat a little bit and put it up here. So in here, we're going to have two constructors. We're going to have shader, and one's going to be a constructor with strings, which is going to say std string shader source vertex shader const std string fragment source. So this is going to be a constructor that builds our shader based off of a string that contains our source code, our fragment source, right? And then there is going to be a shader, which is going to take a path, a file, vertex path, and path, fragment path, right? So the reason we do this is because right now we're building it with inline strings. We want to get it working with that, and then we're going to load it from file. So there's going to be a bind function, which basically will be a function that we call before calling. We're going to have some private functions in here. So there's going to be load, and this is going to just take the same thing as here. It's going to take void load, and then also in our private here, we're going to have a GL uint. Again, I guess I got to include glad. We're going to take a GL uint, and this is going to be a shader module. Right. So you can kind of see how a lot of this is going to work. We're going to generate all these functions, and we're gonna comment some stuff. So here we're just gonna call load vertex source fragment source. So the reason we do it this way is because we're also going to use the same load function inside this one, but we're going to get the source from our files. So we're going to say we're going to load sources from files. So we'll just put the string vertex source, fragment source, like this. And then we will, at the end, load our shader. load vertex source fragment source, like that. Both. So that's most of it. So the way this is going to work, our load function is literally just going to be what we had inside our mesh, what we put in our mesh function. And this everything to do with a shader, which is this. Put that here. All right. So here we just replace vertex shader source to that, fragment source to. I think I can do vertex source.c string. I think I can do that. Can I do this? Like that? No. Yeah. I need to. Like this. Vertex shader code, like that. We need IO stream inside here. Oops. What else? That's done. So we need the same thing, but F shader code will be fragment source.c string. F shader code. Shader program. Actually, I misnamed this. I thought it was shader module. We'll just call it shader program. There we go. Now in our bind function, it's going to be in our mesh.draw. You see we bind our shader. We will literally just bind our shader here. And now what we need to do, we need to create our shader. So in our application.h, now I'm going a little bit fast because I'm not teaching you the language. I'm just teaching you the concepts, and this is fairly straightforward stuff. We're just moving all the shader stuff into its own class. So here we're going to say shader, because like I said, we only need one shader. Number includes shader. Oops. Now it's going to give me the same no default constructor thing, but we'll do that. Shader equal default. And in our application here, we'll say, where do we have our shader code? Shader code. Oh, we have it in our mesh. So we need to take the shader code back out of the mesh here. Put it back into our setup scene. And then we will say shader equal shader vertex shader source fragment shader source. And we want this as a stood string. So we can just, instead of auto, we can do stood string. Like that. Boom. Now we have our shader, and then here you'll see we draw our mesh here. Before we draw all our meshes, we can bind our shader. Like I said, we can use the same shader for all of our meshes, so we just need to bind it one time. Now in theory, if I did that correctly, we should have our own shader class. And it should be giving us exactly what we had before. Boom, same thing. Exactly what we want, right? So we're good. So now I don't like having these shaders inside my as strings like this. I would much rather have them inside files. So we are going to create a new folder inside our project here, new directory shaders, and we are going to say we're going to create 2 new files. We're going to say basic shader dot vert, which is not verty, vert, and new files basic shader dot frag. Add that. I'm going to install these plugins, this GLSL plugin. And what this is going to do, it's going to make it so that when I paste this stuff in, so our vertex shader, I think I already have it, but okay. All right, where is it? Our application.cpp. So this is our vertex shader. We can take everything inside here and put it in our basic shader.vert. And you see now that we in at least in my editor, now that I have the plugin installed, I start getting highlighting and stuff and auto completion, which is one of the reasons why I am doing this. And we will put this in .frag, and we are going to move this like this. Now in here, what we're going to do is we're going to say should file system get current working current path shaders slash basic shader dot. So I'm actually going to just make a path, a shader path, this, and do this, just so I can, not this, this, like this. Whoa. So this is why I use the file system APIs, because we can build paths really nicely. So current path is your build directory. So you're gonna see if I run this, it's gonna fail. Well, it's not gonna fail because I don't have the shaders there. But assuming that of course it failed to link because I didn't do anything. But assuming that this that my constructor was finished and it tried to load the file, it wouldn't find the file because the application is not running from in here, our source directory. It's running from our distribution directory, which is here. Debug is where it's happening right now. So you'll see that we have, we should have it, where is it? CS-330 showcase app.exe, but it'll be inside here. Now what we need to do is we need to copy our shaders from this directory into wherever the exe is running from. And to do that, we will do two things. There's going to be two ways of doing it. I'm going to do it the CMake way first, and then I will go in and we'll do it the Visual Studio way, which is a little bit trickier, but not too much. So let's see. So in our CMake lists here, what we're going to do is at the bottom, we're going to say add custom command. And our target is going to be our project name. And we're going to say it's a pre-build command. The command is going to be a CMake command. And we're going to say copy directory. And what we're going to do is we're going to take the CMake source directory slash shaders, and we're going to put it in the, and this is a little bit complicated, target file directory colon project name slash shaders. Now, usually I would put this inside an assets folder, but I might move that later. So now, assuming that that is done, that should be the correct command. Sub command failed. Showcase app shaders. CMake current source dir. There we go. This should be it. I think I got it right this time. Yeah, okay. So now we got it in. And you'll see now that if we go into debug here, we've got a shaders folder right there. And these have our shaders inside. So now every time we rebuild our project, it's going to copy the shaders into that folder. Now let's do this for Visual Studio. And now this is one of the rare times I'm going to go in and I'm actually going to do this middle of a lesson. We're going to do Visual Studio here because it's a little bit annoying. Okay, so inside here we go properties. Now we're going to say build events, pre-build event, command line, and this is going to be xcopy quote $, parentheses projector, like we had before, and my folder, which is going to be shaders, and then backslash star, meaning anything inside that folder, quote, space, another quote, $, parentheses, target there, shaders. This, then /y/i/e. Now I think that's going to do what it needs to do. Hit apply. Now let me find that folder. So we're running inside this x64 debug folder, right? So we're expecting it to show up there. So if we build this now, you're going to see it just showed up. Showcase x64 debug here. And our shaders are in here. Unresolved shader. Oh, okay, so I didn't, and also because I didn't add the existing items inside here, let's add shader and add existing item. Oh, I added shader.cpp in the wrong place. I include shader.h. All right, so let's move this into this filter and move this into this filter. Now, in theory, everything should be building properly. Yeah, this works. This worked fine. Done, build succeeded. And it copies everything into the correct folder. So we need this because when you're trying to load files, into a C++ application, it always checks from your run directory. That's what that's doing. That's copying it into your run directory. Now I'm gonna do one more thing in my CMake folder because I don't like having everything nested so deeply. What I'm going to do, if I can find it, is a command here. I'm just going to copy paste it just because it's kind of annoying to put. But here, we're going to say, we're going to add, we'll put this at the top. We're going to set the CMake runtime output directory to the CMake source directory, CMake system name, and then also we're going to say project name. Like this. No, we'll ignore that. Like this. So what this is going to do is it's going to take it out of this nest and it's going to actually bring it to the top, which means we're going to need to add more to our git ignore. Well, let's build it first, and you'll see what I mean. And now you'll see here it gave me a dist folder that has all my applications inside. That way, it's just easier to find my exe files. It just makes it easy. All right, so with that done, let's go back to our shader and start loading from file. Now what we want to do, we're going to create a couple streams. We're going to say std if stream, so file stream of b shader file, std input file stream, f shader file for fragment shader file, and we will include f stream because we need to be able to work with file streams. Then we are going to try opening vshader file, open vertex source, and fshader file, open fragment source, like that. Catch should if stream failure e, and I'm just gonna copy this from this, and we'll probably want this as a reference, like that. So we failed to read the file, it will throw an error, and then just yeah, it'll print it out, and we'll know it's not working for a reason. So now we will create string streams out of those file streams. So string stream, shader stream, shader stream, and we'll say if vshader stream into from vshader file dot buffer, read buffer. Same thing with fshader stream with fshader file. Then we're going to close the files. And then we will actually just call load from here. And we'll call load like that. And vertex source. So maybe I don't need this. Can I do what is this dot string? Yeah, like that. Fshader file string. Fshader stream. I don't need these. Why did I move all of these? I'm dumb. These need to be underneath here for one. I don't know what I was doing, why I was doing it so high up. What? Move these up here, and this will be vertex path and fragment path, like that. And these can be const references. Well, that's what this why it's yellow. It could be const references. All right, I like cleaning stuff up as things are pointed out to me by either the editor or if I notice them. So what the hell is going on with my there? Shader.cpp. All right, so now it should load from file. All right, now if we build this, so this is just simple file loading in C++. We're loading a file. We're opening the file, reading it, basically taking the stream of the file into a string stream, and then putting that stream into a string. And now we're loading from file. You'll notice that everything worked properly. Now, if we change a shader, not in here, but in our folder here. Now, let's say we want to just add blue to everything, right? Or let's say not blue, because we put X, Y, and then vertex color, and then we'll say RGB, yeah, blue. We're gonna just max out the blue value on all channels, on all vertices. We do that. Just as a caveat, when you do this, there's been no code changes, so you won't see a difference when you just make a shader change. This is just in the nature of this pre-build command, or even the same thing in Visual Studio, the one we did, it's a pre-build command. So if there's nothing to build, it won't do anything. So go into like your shader and just like add a space to test it. And you'll see that it'll do a build, which will trigger the copy. And then you'll see that everything is now blue. And you know that everything's running from our files. All right. So, and just to, no, I'm not going to do it, but it'll work in Visual Studio as well. I want to verify that information, because if I don't verify the information and it doesn't work, you guys come to me, and I don't have time to do this much. And it's kind of a pain in the ass. So, all right, so let's build this. It should, yeah, 2 files copied, and it should come out blue, exactly the same thing. Exactly the same thing as we had before, so everything is working in both Visual Studio and in CMake. Okay, so now we got those things working. Now we need, what do we need? We will build a cube. That's going to be the first thing. Cube or camera? Let's build a camera. So this will be, let me find the chapter. So it'll be in this transformation section in OpenGL here. It explains how vectors work and how transformations work a little bit, how everything's to be stored in a matrix, how you multiply matrices together, how translation, rotation, matrix, and stuff like that works, and all that kind of stuff. It's cool enough. But what we're going to do for now is we're just going to we're going to ignore this transform stuff for now, and we're going to add a camera that will move, that will do perspective. So in the end, this GL position, right now we're just converting it directly to clip space, which is the space that is presented by the window. What we need to do is we need to have all the vertices defined in 3D theoretical space, and then have it transform itself into the view that the camera would have. So the way that's going to work, and we're going to do this in a very simple way, this one, just so we can get the general idea of it. And this uses the transformation stuff we just talked about. We're going to implement a very basic camera. So in our application class, width, height, let me find something width. We actually want to keep these, and I don't know why I didn't do that before. Fudge. Okay. All right, so we need to store these width and height variable whenever our window gets resized, because we're gonna need the width and height to determine the way the camera is set up. We need the aspect ratio specifically. So what we need to do is we need to be able to access our application class from from this callback. Now the way you would do this is you would do there's a function called glfw set window. Come on. Set window user pointer. Yeah, this is it. And then you will call window, and then you will give it a void pointer to whatever you want to be able to retrieve from inside your callbacks. So I'm going to give it this, right? So that means it will have access to the different stuff. So now when I'm inside here, I can say glfw get window user pointer from our window that the callback is being triggered from. And that returns a void pointer. So we can cast that to a application like that, and we can just say app like this, and now we can say app width, app height, and now we can set those values. Now this is just a side effect of just the way they're doing callbacks, because I can't just pass in this here. it just doesn't work because it's an old style function. It's not a std function. Oh, that's just the way it works. So we need that. Now that we have that, let's we can start defining our camera. So what we're going to do is here is in our draw function, we're going to do this every frame. Eventually you would have a camera object that you would move around the scene to do this kind of stuff, but we're going to do it this way. So we're going to define a mat4, which we're going to define a mat4, which is a 4x4 matrix, which is going to be our view matrix. And this view matrix is going to be equal to glm look at here. And now we don't have access to that function. I'm just going to paste some stuff in just because I don't feel like typing it all out right now. It takes 3 vec3s as look at, what is it? So remember, include glm slash d bpx slash matrix transform g btc matrix. Is it this one? I think I was right. Good. All right, so we have look at now. All right, so I just did that so I could know if it was working. So if we look here, it takes the eye position, which is our camera position. So what we want to do is we want to take our camera. Go back here and delete this. Delete this. So let's say we have if we're looking at it now, so you need to think of this in 3 dimensions. So this is z. This is x. Now I'm labeling them in the positive direction, so you know what zxy. So we need to move the camera this way back on the z-axis so we can look straight into the scene, right? So we don't want to move it side to side on the x, and we might want to move it up and down, but for now we'll just move it back on the z-axis for now. So we'll put a glm vec3, and we're going to say 0, 0, and -5 here. Now, center is where we want to look. So our camera is going to be here, be at -5 on the z-axis, and we want it to look this way to 0, 0, 0. So the look direction is 0, 0, 0. Finally, the last parameter it wants is the up direction. So which direction is up on the camera? So this defines, because sometimes some coordinate systems, the z-axis is pointing up, some of it, the x-axis is pointing up. We want the y-axis to point up. So the way you tell that is by giving a positive direction y, so 0, 1, 0. And that will tell it that we want the camera to be 5 units back on the z-axis, looking to the origin, and the up direction is towards the positive direction on the y. For the projection matrix, what we need to do is we're going to have a field of view. We're just going to do we'll say a 75-degree field of view for now. So it'll be glm mat4 projection matrix, well, glm perspective. Now what does this take? This takes a field of view in radians. So you want to convert it to radians, which there is a function in glm4, glm radians, and it'll be 75 degrees in radians. The next one will be the aspect ratio, which is why we needed the width and height. So we'll just say float width divided by float Right, now usually I would use static casts for this type of stuff, but I'm kind of just starting to get lazy. I'm getting tired of talking, recording all these videos at once. The near and far is where the distance before it starts clipping and cutting geometry out. So if you're really close to an object, how close can you get to an object before it stops rendering it? Because you don't want it to render something that's like right in front of your nose or like basically touching you. So we're going to use what's provided on Learn OpenGL is 100.f and 0.1.f. So that's your view and projection matrix, right? Now, finally, the model matrix, we're going to call it. The model matrix, there's one for every mesh, but basically the transformation in space for that specific object. Now, we're not going to move our objects yet, but we can define them like this. Mat for model equals GLM mat for, and we create an identity matrix, which basically means no translation, no transformation at all. Just do it like that, right? Okay. So with that done, what we need to do is, okay, so now what we want to do is we need to be able to set values inside of our shader. So inside of our shader, what we're going to have is we need to be able to store these things. So in our vertex shader, we're actually going to define some new things. We're going to define a uniform mat for, and this is going to be view. And then there's going to be uniform mat for projection and uniform mat for model. And then in our GL position, the way this works is you need to multiply the position. So you want to take the vector of position and 1, and you want to multiply that by the model matrix, and you want to multiply that by the view matrix, and we want to multiply all of that by the projection matrix. Now this will, so it goes right to left. So it takes the position and transforms it into model space, which will move it in space relative to the origin. Then it will transform it into view space, which is the model compared to the camera. And then it'll transform it finally into, I think clip space is the last one, but into the final one, which will decide what will give it either depth or no depth and that kind of stuff. So that's what we want to do here, and we need to be able to set these values, right? So these values are currently unset. So what we want to do is inside our shader class, we go inside our shader class, we will now give them some functions to be able to set these values. So void set mat for, and we're saying const glm mat for reference, mat for, and we can include glm.glm.hpp. I find it really weird that it says all of these are not implemented, but I disagree with that assessment. It's definitely implemented. Never used. That's also not true. All of this is kind of borked right now. Anyways, this one is fairly simple. We need to make sure that the program is active. So we say we can just call our bind function. And then once we bind it, we say GL uniform matrix for FB. So what this says is we're going to update a uniform value of type matrix for float values, right? Now here, what we want to do is we're going to need to be able to find the location of we need to get the location of the I also believe we need the name. We also need the name. So let's change the change the definition here. We also need a constant string uniform name, like that. And we're gonna also have a thing here, std string. No, it will be a GLUint uniform location. Get uniform location. And this would be constant string reference uniform name. So the way this works inside of a shader is that you need to get the location of the uniform from the shader when you need it, so that you can properly set the spot. So this is constant reference uniform name. Now we say auto uniform location equal to get uniform location uniform name, and we'll deal with that in a minute. Once we have the uniform location, what we want to do is we will say uniform location, what is size, how many, 1. I think this is Boolean. What is this, normalize? I think this is normalized, so we'll say false. And then with GLM, what we want to do is we want to get the pointer to the value. So we do GLM value pointer mat4, like this. Now we don't have the value pointer thing, so which header is that? GLM, this one. So it'll be include GLM /GTC /type pointer.hpp, like that. And we give this. Oops. Now this was giving me some sort of unsigned int. GLint. Oh, it needs to be GLint? I'm done. What the hell? Sorry. I misread that. We're going back in. You can tell I've been doing this for a while now, so I'm getting a little bit tired. GLint. Okay, that should work. There we go. I had to get rid of that. So now we need to GL get uniform location of our shader program and uniform name string. Will that work? That does work. Good. All right, and we will just return this. So what we also will do is if uniform location is not equal to -1, then so -1 is what it will return. This returns if there's an error. And now, finally, we are getting to the meat and potatoes of this. We will set some stuff on the shader. So shader dot set mat4 projection shader dot set mat4 view shader dot set mat4 model. Now it'll use these values for every single one of these draw calls. Right, so now let's hit play. Now you can see that it got smaller because we moved away, and that you can also see now that everything is properly square because it's using the proper aspect ratio on the screen, right? So if we move this to 2, you can see it moves much closer. Okay, it moves closer. And now we're going to add this model matrix to each of the individual meshes. So inside of our mesh.cpp, we're going to, inside here, we can put, we're going to put it glm map for transform. Now this is, this is not going to be it's going to be a little bit annoying. So we probably want a class for just transforming. But you know what? We're going to actually make this public for now, just to make it easier on ourselves. We're going to do transform, so that when we go to here and after we create, we can remove this. We can move this down here into set map for mesh.transform, like that. And now we can say here, when we create our mesh here, we create our first mesh. What we can actually do is auto mesh 1, and we want a reference to this. Pretty sure this is how this works. Now we can say mesh1 dot transform equal glm translate mesh1 dot transform, and we translate it by a certain amount. So this will be glm vec3. Now let's say we want to move it left 0.5 units, and that's it. Now we're going to do the same thing with the mesh 2, the second one. So we'll remove this and we'll say auto mesh 2, auto reference mesh 2 dot transform, and this one we're going to move to the, I guess the first one we did right, this one's going to be left. So now when we play this, you're going to see that the things have moved. They moved apart. And that's how you have different objects that you can move around independently from each other. So one last thing that you need to know, or you need to work on in this week, is how to build a full mesh. So we're going to build a cube. Now a cube is not that complicated, so we're going to do that first. And now what I'm going to actually do so that we can reuse these shapes is inside my include folder here in types, I'm actually going to close this. I'm actually going to make a struct called meshes, and I'll say inline std vector static inline std vector vertices, cube vertices. Will that work? Vertex. Oh, that did work. And static inline uint32t cube elements. Okay, and now we're going to start building out a cube. Now this cube is only going to have position and color right now. The normals and UVs are ready to go whenever you need to add them, but we'll do this first. So let's start with just laying out a cube. So first we have 1 cube, 2 cube, and these go together. Now we need to number all of these so that everything makes sense afterwards. And remember that everything needs to be done in counterclockwise order as well. Okay, so that's our cube. Now in blue, I'm going to mark the different triangles that I am going to go for. So it's going to be like this. Do this one. So it's going to go bottom right to top left on all of them, except for the top one. Bottom right to top left. So you see that this one here looks kind of weird, is because I'm looking at it in my mind from the other side. So if I flip this cube around, this will be on the right side and this one will be on the left side. And this one is bottom right to top left. And bottom right If I flip this one to the top, it would be bottom right, the top left, like this. Okay, it's a little bit hard to see now, but let's label our vertices here. So as I'm just gonna get rid of these. That makes it a lot harder to visualize. So I'm gonna number these. We'll do one face at a time. So we'll do the front face. So this for the front face, it'll be 0, 1, 2, 3. Okay. Now every face is gonna have four vertices. You're not good, as I was explaining in the last video, because of normals. You need all the vertices that have the same normals on the same face. So that's what we're going to do. This front face is going to have 4, side face is going to have 4. So I'm going to do these 4 first. So 0, 1, 2, 3. So let's, I'll make these side by side. And now we're going to do the same thing we did before, where our axes are going to be in the middle, like this. In the middle on the z-axis going through. It's not quite in the middle, but I mean, you get the point. And then x, y, right in the middle, right? So everything's going to be based on 0.5. And yes, I know that technically this should be, oops, damn it, blue. But yeah, just judge everything in the middle. So our first one is going to be minus 0.5 x. So let's just put let's start defining the vertices. Position equal like this. 0. So actually, we can, everything's going to be 0.5 or minus 0.5 on this example. So we can actually just do this. And then we can just change pluses or minuses as we go. So and we can put comments here to be clear. Front face. This. 3, 4. All right, so we got 4. And let's close this because we're going to be in this file for a while. Okay, so the first vertex, we're going to start with 0. This first vertex is going to be minus 0.5, 0.5, and plus 0.5 on the z-axis, because remember, z is 0 in the middle of the cube. 1, it's going to be minus 0.5, minus 0.5, 0.5. And then the 2 is going to be 0.5 minus 0.5, and then 0.5. And then it's going to be 0.5, 0.5, 0.5. That's our front face of the cube. Now our indices, it's same thing as last time. We're going to say we want bottom left to top right. So 0, 1, 3 is going to be the first one, 0, 1, 3. And then 1, 2, 3. 1, 2, 3. Front face. Right? All right, now let's do the right side. Now remember, our indices are staying starting at 4 now. So this top left corner is going to be 4, 5, 6, 7. Now, same thing as before, we can actually just copy all of this here. Actually, we actually want to copy the one with all the positives, because it makes it easier. We can just add minuses where we need them. So it's going to be plus 0.5. So x is going to be plus 0.5 on all sides. So you're going to realize that every face, one of them is going to stay the same all the time. Either the y or the x or the z is going to stay the same. Y is plus 0.5. And z is plus 0.5. So yeah, so because this one is the same as this one. Makes sense. Now 5, x is the same. It's minus 0.5 on the y and plus 0.5 on the z. 6, same, minus 0.5 on the y, minus 0.5 on the z, and plus 0.5 minus 0.5 on the z, and then we're done. Same thing, 4, 5, 7. 4, 5, 7, because we're going, remember, I'm drawing all of my my triangles like this, bottom left, right, top right. So if we do that on this side, it's 4, 5, 7 is one triangle, 5, 6, 7 is the other triangle. 5, 6, 7 is the other triangle. Right face. Now let's do the back face. Back face, and then I just got to remember to. All right, back face. So 4, 5, 6, 7. So we start at 8. So if we use the same thing, 8's going to be this one. 9, 10, 11, like that. So how are we doing this? 8 is going to be, so Z here is going to be minus 0.5 on all the Z, because the Z axis is the same everywhere. So X is going to be minus 0.5, 0.5, and 0.5, so that's good. And that should make sense. It should be the same one as the last one. That's how it's set up, is the last one on these should be this first one on the next one, it looks like. 9, so it's plus 0.5 and then minus 0.5 on the Y. Then it's minus 0.5, minus 0.5, and then it's minus 0.5 plus 0.5. And then when we do the back face, it's going to be, so we're doing it like this. When we turn it around, it starts at 9 to 11. So 8, 9, 8. Yeah, 8, 9, 11. 9, 11. And then it's going to be 11, 8, 9, 11. So 9, 9, 10, 11. 9, 10. Yeah, 9, 10, 11. This will be back face. All right. We're getting there. We're getting there. This is, and you're going to have to do this with all of your, so we're going to do left face here, position here. All right, we're getting close. We're getting much closer. All right, so left face again. We start at 12 now, so it'll be 12 here, 13, 14, 15. Now 12 is minus, so X is always going to be minus 0.5 on this one, so we can just do that. The Y on this one is going to be plus 0.5. I took the negative, that sucks. And then the Z is going to be minus 0.5. Then 13 is going to be plus 0.5 on the Y and negative 0.5 on the Z. Then the 14, the Z comes forward on the next two, and then it stays negative 0.5 on the Y. What? 12. 13 is negative 0.5 on the Y. 14 is negative 0.5 on the Y. And 15 is positive 0.5. And then negative Z, positive. Okay, that's good. Now, we do the indices. So it'll be 12, 13, 15, 12, 13, 15. And then it would be, I think it's 13, 14, 15. Yeah, 13, 14, 15. 13, 14, 15. Left face. And 2 more to go, and we should have a cube. And you're going to notice there's going to be one issue when we're done this cube that we're going to want to deal with, but we'll get there. All right. Now let's do the right face. Now let me give me all positive stuff. Where's all the positive? Positive. All right, top face. Top face. All right, now the Y is going to be the same on all of them. So so this one's going to be moved a little bit. So top left is here. So it's going to be shit. What was shit? 15, 16 is where we start. So it'll be 16, 17, 18. Oh no, 18. I want to do the same pattern on all faces when you're looking straight on, so that when we're doing the winding order, it's easier to do. All right. So top face. So like I said, Y is going to be positive the whole time because it's at the top. X for the first two is going to be negative 0.5. Second two will be positive 0.5. Then it will alternate Z. So it'll be negative, positive, positive, negative, like that. I'm moving a little bit faster because we've done a few now. You should kind of get the gist of what I'm doing. And then this will be 16, 17, 18, 17, 18, 19. Top face. And then finally, 20. Oh, why did it change sizes on me? God dang it. Why did you change sizes? 20, 21, 22, 23, like that. All right, and now it's going to be bottom face here. Bottom face. So again, Y is going to be the same across, but they're all going to be negative this time. So we'll start with this one, all negative. X on 20 and 21 are positive. And then 22 and 23 are negative. And then Z alternates from positive to negative, negative, positive, like that. And then finally, it'll be 20, 21, 23, 21, 23, and 21, 22, 23. All right, now assuming we didn't make any mistakes, we should have our cube completely defined here as a static ability here. So now I think I used move here. I'm actually going to go back and change that because I don't want to move these in because they're static. So I'm actually going to remove this here. I don't want to move these in anymore. So we're going to remove these double ampersands. And you're going to see me do this sometimes. Sometimes I'm going to revisit some decisions I make as we go through and I think about it a little bit more. So now I don't want move. We don't want to move these vertices like that. And we're actually going to remove all of our meshes now that we've got this pretty much covered. And we're going to say meshes dot in place back. Now, what did I call these? Meshes. I want to call these predefined objects. Predefined object. There we go. Or actually shapes. I'm going to call these shapes. Now in my application, I'll do shapes. Dot. All right. I need to include type. I do have types. Why don't I have shapes here? There we go. Cube vertices. Shapes. Cube elements. Like that. There we go. Now in theory, if everything went right, we should have a cube. It might not look like a cube very much yet, but that is giving us a good idea that it's probably a cube. Now, if we want to double check that we can move our camera a little bit to the left. So we'll move it, let's say 0.5 to the left, and we'll move it we'll move it 1 up. This will make it so that we should be able to look at it from an angle which will give us tell us that it kind of looks like a, yeah, see the shape of the cube is there, which is good. So we got the shape of our cube basically going. Now we have a perspective camera, which is good. And in our shapes, let's define some colors in our shapes. So you see all these vertices here. We're gonna make a different color for every face. So we're gonna say red on the top. Red, more red than anything else on the top, I should say. And then on the, and that's not on the, that's the front. Then we will, just so we can see the different faces, I'm just going to put different values here. On the right, on the back, we will do 1.f in 2 places. Okay, now on the front, we'll just make this 0. We'll also make this one 0. Top. Now we'll make this one 0. Make that 0. Make this one 1. Make this one 0. All right, and we'll make all of the one side pretty much black. 0 point, or we'll make it partially blue. Now when we run this, we should be able to see it. All right, so now you're going to see some issues here, which is one of the issues that I want to see. Seems a little bit off, but this is normal. So one thing that we don't have enabled at the moment is depth. So we can see through stuff basically, and they don't know what is in front of what, so it has trouble figuring out how to draw stuff. So it's pretty easy to enable depth in OpenGL. All we need to do in our application when we open our window, in our open window here, we want to, here in our, after we start open the context here, we want to enable our depth testing with GL enable GL depth test like this. And then when we do our GL clear, when we clear the color here, we also want to clear the GL depth buffer bit. So that, just doing that should resolve most of our issues, I believe. No? What happened? Oh, I didn't. You have to do it after you do the GL loader. I don't know why I put it so high up. Now, okay, so we still got something broken here. My top face is not correct. And what about my, it looks like my bottom face might not be correct as well. Let's bring this down as well so we can look up on the object. So the bottom is good. The top is broken. So we're moving it to the right. So we're looking at the left face. The left face looks like it might be kind of busted too. No, the left face is fine. Okay, now let's look at the back face by moving the camera to the front of the object or to the back of the object. Yeah, so the only one that seems to be broken is my top face. Yeah, so my top face is broken, and the color on my left face seems to be screwed up too. So we'll find left face. The color is here. You can see that they're not all the same. The left face color is fixed. My top face indices are wrong. 16, 17, 18. Oh, that's wrong. 16, 17, 19. It should be. Boom. And now we have a perfect cube. Now, if we want to make this really interesting, now that we have it, we know there's only one mesh, so we'll do this here. Actually, we'll just make it. We'll do it for all meshes. We'll say mesh dot transform equal BLM rotate mesh dot transform angle. So I think this is supposed to be in radians. So we'll do this in 0.001. And the up BLM vec 3 0 1 0. Oh, okay, that did it. I just putting that F there did it. All right, so this should cause it to rotate a little bit every frame. Maybe that number is too small. Oh, so all right. So what I'm doing, and the reason why this is not working, is because I'm not getting a reference to the mesh. So when I'm overriding the transform, it's not. It's just overriding on the copy. So because 1 degree every frame is going to be too much. How's this? And now you see it's rotating a little bit slowly. And we'll move this back to the center. And we'll move this back to the front. Oh, -2 is fine. There you go. Now it's rotating along all the sides. I'm too high up. I want to be here. I want to move a little bit further back. And you know what? I will also see if I can rotate along the X as well. There. Now we can see the cube rotating in space. And you can instantiate as many of these cubes as you want. When you create any other objects, you're going to do everything the exact same way. So when you make your pyramids, your spheres, you make your indices and your vertices, and then you have your object. Anyway, this was another long lesson for week 3. Longer than I anticipated, but this should get you pretty much where you need to go. This went from start to finish for quite a bit. So I hope you enjoyed what I did here, and see you next time.